This is Mr. Dahlstrom's take on helping out some problems from the AP Physics homework, specifically about number 43 and how to apply the parallel axis theorem to try to figure out the moment of inertia or the rotational inertia of this design here. So what we have here is this is sort of difficult because I'm trying to show 3 dimensions on 2 pages. We have some different axes here. We have the y-axis here. We have the z-axis, and then we have perpendicular to both of those, the x-axis. Now, what this problem is asking us for is to figure out what is the moment of inertia, not about the center axis, meaning if I were to just rotate this one here, but instead of being in the y, what if we were to move that to the end of this so we were rotating about that? So basically this whole entire thing would be rotating about this axis right here. I do have sort of a little design I can try to help. I made this, hopefully I can help you a little bit. Let's see if I can organize this a little bit. So I did make this in my spare time. This is sort of a representation of 3 rods that we have here. So we could call this here, I'm going to use it, sorry, see right here. We can call this one right there the y-axis, so that's the original axis here. Here would be the x-axis there that we saw that was orange, and then this one would be the z-axis. So we can, right now, if this is the y-axis, we can rotate it about this axis, and it's fairly easy to do that. So what we're going to eventually find is we're going to try to figure out what is the moment of inertia about this axis here, and then instead of rotating about the axis, here, we're moving, with my camera here, we're moving that axis. Instead of being there, we're moving it down to here, and we're going to be rotating this thing about that. So instead of rotating about a central axis there, we're moving the axis. Some might say that we're moving it parallel to the original axis, and we're going to try to figure out what the moment of inertia is for there. So let's go back to the problem there. Move my camera around back to the original setup. So once again, where we're trying to show there that the y-axis, we can rotate that, but we don't want to do that. We're going to move the axis, and specifically this axis is parallel to that and rotate it about a new one. So the must-knows to get started for this, the first thing is to know what is the moment of inertia of the center of mass of a thin rod of length L about the center of mass. So what do I mean about that? If that's my thin rod of length, I'm talking about from the center here, what is the moment of inertia. Now this is something that we would have to be given. The book gives this here, and so it's given as 1/12 ml squared. So a single solitary, so let's look at the red one, a single solitary, if we were to rotate it about this axis right there, around that axis, that is 1/12 ml squared. About the axis here, that would be 1/12 ml squared, and that would also be 1/12 ml squared. The other one is to know the equation for the parallel axis theorem here. Now, I was a little bit there. We do have 3, so we have 3 rods here. Also, each of them have a mass of m. Now, one way to approach this is the first thing we need to figure out is what is the center of mass, not just of one rod, but all 3 rods about the center of mass here. Now we're rotating it originally around this y-axis here, so this is the original. And the thing about if you're rotating about a thin rod, when we say by thin rod, is they're saying, yes, technically it has a radius here, but we're assuming that the radius is so thin that we can approximate that if we're rotating about this axis here, sorry, I should probably be using the right color. If we're using about this axis here, as long as the axis goes straight through the middle, we can approximate the center of mass, the moment of center of mass, about the red axis as being 0. So one way to approach this to figure out, first of all, what is this, is to say, okay, what are the sums of the center of masses of each of the objects? So what is the sum, or what is the center of mass about the x-axis, plus what is the sum, or what is the center of mass about the y-axis, and what is the center of mass, moment of center of mass around the z-axis. Now I said here one thing you need to know is that a thin rod length L about the center of mass here, the x, so what we're doing here is we're rotating it so that this x value is, let me move this up way a little bit, that this X rod that's here is being rotated sort of like that. And if it's being rotated about center of mass there, then that is what we're going to be using. So that's 1/12 ml squared, okay, because about this center axis here, it's being rotated about that. So basically have this is rotating about that axis, and so that's 1/12 ml squared. Now we look at the y-axis, and this is what I mentioned here, that if the axis goes straight through here, we're assuming that this is a thin rod, and so even if we were looking at ml squared, if we were looking at a rod where we had something where it was mr squared, we're approximating that this r is approaching 0, so there would be no moment of inertia there. So for the moment of inertia around the center of mass of the y-axis, that would be 0. And then for the z-axis, in a similar way, we have it on this axis, and it's rotating about its center. And if it's rotating about its center, we have, once again, we have 1/12 ml squared. So we can simplify this, that the center of mass of our object is 1/12 plus 1/12. And I'm going to keep 2/12. One of the reasons is that the answer is in terms of 12ths. So we have our center of mass. We have just figured out this value right there. Okay, so now we move on. And we want to know the moment of inertia, not about this center axis. We want to say, what if instead of there, we were to move, I'm trying to find a different color pencil. What if instead we were to move where our axis of rotation is? What if we were to move it that distance right there? We were to move it a distance. So once again, this is here, moving it there. You can imagine that I'm sort of just displacing, or in here, I'm moving along the X rod here to the very end. Okay, so we have I is equal to ICM, which we just calculated is 2/12 ml squared, plus md squared. Now, what is the md squared? What does this d mean in the first place? This d means how far have we moved from our initial axis of rotation. So how far have we moved? If we were originally here, okay, on the x-axis, on the x rod in the middle, and we moved this far. How far is that? It's not. If this is L, then that means that that distance that we displaced ourselves is L over 2. So down here, let me just have a side over here. So md squared. And other things. We have to also remember that there's not just one rod here. There are 3 rods, and each have a mass of m. So also this mass becomes 3m to represent that we are basically taking the whole mass of all those. D, in this case, we have displaced ourselves not the whole length, but just length over 2. So that's L over 2, and that is squared. Okay. Let's go ahead and simplify that. That ends up being 3/4 ml squared. And then that's what goes right there. So we have 3/4 ml squared. So all we have to do is simplify this, and we have our answer here. So 2/12 ml squared. 3/4 in terms of 12 is 9/12 ml squared. 2 plus 9 is 11/12 ml squared, and that is the moment of inertia around the axis, not through the center of the y, but one that has been displaced parallel to the original axis, and that is a good example of an application of the parallel axis theorem. So once again, some things that we needed to know. We needed to know what is the thin rod moment of inertia about the center of mass. That's 1/12 ml squared. Either that's something, what I've done is I've just memorized what those are. I've memorized that that's 1/12. I've memorized what a disk is, and I've memorized what a sphere is and a hoop, instead of having to necessarily use integrals to derive those. So once we realize down here that the x-axis would be 1/12 because it's rotating about its center of mass, so 1/12. Y, it's not rotating about its center of mass, it's rotating along here, and we're assuming that this is a thin rod where any coefficient times mr squared, if r is assumed to be 0, a very thin rod, then we can approximate this as 0. This is only an approximation, but it's a very good approximation, especially for a very thin rod. And then it's similar for z, since we're rotating this about the center of mass, that's also 1/12 ml squared, and that yields the center of mass of the object we're originally dealing with. Where the parallel axis theorem comes in is that we are basically taking that rotation here and we're just shifting it out, and that's where the md squared. So once again, what does d mean? It's how far you have moved away from the original axis of rotation. We had 3 rods, each with a mass of m, so that's where 3m came from. And we displace ourselves not L, but L over 2. And then you substitute and solve for that, and we get I equals 11 over 12 ml squared. So just a little lessons today. We'll follow up on a different problem in a few minutes. Thanks.